Welcome student to week 11 of course Hydraulic Engineering. This week we are going to study topic called Introduction to Computational Fluid Dynamics. This is in continuation to the last week's module where we studied viscous fluid flow and we derived the Navier-Stokes equation. So computational fluid dynamics is nothing more than solution of this Navier-Stokes equation. The Navier-Stokes equation is quite complex, so there are different ways of solving those. So this module is dedicated to that. Since this is an undergraduate course, we are not going to give you too many details, but at least touch upon all the basic concepts of computational fluid dynamics. So let's get started with this. So the first question that is very common and very obvious that you should have in mind is, what is CFD? So the analysis of practical fluid flow problems involve two fundamental approaches. Okay, so if you try to solve any practical fluid flow problems, we can use two approaches. One is experimentation and the second is the calculation. So experimentation requires the constructions of model which are tested in various facilities. One topic we have already said and read in this course was dimensional analysis. Dimensional analysis is very critical to this experimentation, because when we do the experiments in the lab, to be able to apply those in real life, we need to study dimensional analysis. And as it is written here, experimentation involves the construction of models which are tested in various facilities, whereas calculation involves solution of differential equations. Whatever the differential equation of the problem that we form, that is the solution to that differential equation, is called calculation. So this calculation can be performed in two ways. One is analytically, or the second is computationally. Analytical is mathematical solution. For example, like you solve the integral equation by hand using the formulas of math. Computational is using the computers. So the field of study devoted to the solution of the equation of fluid through the use of computers is called computational fluid dynamics, or CFD. Okay. So this is a very crude definition, but at your level we can say that the field of study devoted to solution of the equations of fluid flow through the use of computers is called computational fluid dynamics, or CFD. So the equations of fluid flow could be Euler equation, Bernoulli's equation. So they are in a broad sense termed as CFD, but in reality the solution of Navier-Stokes is called computational fluid dynamics, or CFD. C stands for computational, F stands for fluid, D stands for dynamics. All right. In this field of study called computational fluid dynamics, experimental results are used, and they are often used. And what is the purpose of using those experimental results? They are used for validation of the CFD solution. So if we get a computer based solution from the equations, we use computer to solve those equations and we get some answers, results. How do we know if it is correct or not? So what we generally do is, we do the mathematical calculations for the same situation as one of the experiments had been done before. Either we do that experiment in the lab or somebody else might have done, but beforehand we know the experimental results of a situation. for the same situation we do computer based solution, and we try to check if the results that we have got from the computer is the same or very close to the experimental results or not. So, this process is called validation. Validation means, so it will validate, it will justify, or this will say that okay, the CFD solution is okay or not. So, if the code or the solution is successfully validated against experimental results or a real life field study, that process is called the validation of the CFD solution. So, computational fluid dynamics can handle laminar flows with with ease. It is not a problem at all. The problems become complicated when we have turbulent fluid flow. So, the CFD solutions for turbulent flow situations are much more complex. All right. The accuracy of the turbulent CFD solutions depends on the appropriateness of the turbulence models. So, we will later study in this module that there are something called turbulence model. Okay, just to name them, one is K epsilon, K omega. There are different model. So, these are called turbulence model. There is something called, which cannot be actually said turbulence model, but a different way of solving this technique is called large eddy simulation. There is something called direct numerical simulation. So, the accuracy of these turbulent CFD calculation depends which model are we going to apply. We will see that direct numerical simulation gives the best results, most accurate results. Large eddy simulations give the second best results, and the last is Reynolds average Navier-Stokes equation. In Reynolds average Navier-Stokes equation, there are different turbulence modules, but everything comes with a cost. For example, you must just know that direct numerical simulation, although it has the best accuracy, but the time of computation that is required is extremely high. So, large eddy simulation are the second best in terms of accuracy, but cost wise it is also very high, of course less than direct numerical simulation. Whereas Reynolds average Navier-Stokes equation has lesser accuracy than the above two, but the time of computation is far less than what these two type of models in CFD takes. But we will come to those later as well. So, this is what it means. The accuracy of the turbulent CFD solution depend upon the appropriateness of the turbulence model. Which turbulence model is appropriate? Now, going to differential equations of the fluid flow. So, the differential equations of fluid flow are, we have been going through this from a long time now. One is continuity equation that we have seen, for example in compressible flow del dot V is equal to 0, all right, which we have seen actually in the last week's model lectures on viscous fluid flow. And the second is the Navier-Stokes equation. So, these are the two equations, differential equations of fluid flow, all right, and the solution of these equations through computers is called CFD, computational fluid dynamics. So, the aim of CFD is to seek the solution of these equations for practical flow situations under consideration. You remember when we started this lecture, we defined CFD, the use of computers to solve the fluid flow equation, right. So, these are the fluid flow equation that we were talking about, all right. Continuity equation and the Navier-Stokes equation, and the aim of CFD is to seek the solution of these equations, and it should be for a practical flow situation. We should not assume say a velocity of 1 lakh meters per second or something like that. I mean, the simulation should be very much practical in nature, like a velocity of 1 meters per second, or a wave traveling with a wave height of 1 meter. If we assume a wave height of like 100 meters, it might not be very real, for example. All right. So for an incompressible flow of a Newtonian fluid, this is the continuity equation. Del dot V is equal to 0, and this is continuity equation or the conservation equation. All right. The second equation, if you can remember, what is this? Yes, this is Navier-Stokes equation, which is actually a transport equation, and this Navier-Stokes equation is for incompressible flow. All right, this one. So as I said, Navier-Stokes equation can be classified as transport equation, and continuity equation can be classified as conservation equation. So this transport equation transports what? It is a transport of linear momentum. All right. So for 3-dimensional flow in Cartesian coordinates, there are 4 coupled differential equations involving 4 unknowns. So if there is a flow which is occurring in 3 dimension, there are 4 different equations, all right, which involves 4 unknowns. So one of the unknown will be the velocity in u direction, the other is going to be the velocity in v direction, and the third one is going to be velocity in w direction. Okay, all 3 directions are velocities, and the fourth one is going to be the pressure. All right. So these are the 4 unknown, as it's already written here, u, v, w and p. And if there are 4 equations, there are 4 variables u, v, w and p, there are 4 coupled differential equations. So these are the 4 equations. So this is nothing but del dot v is equal to 0, as it is written, del u by del x plus del v by del y del w by del z. So now you would understand why I taught the viscous fluid flow lecture before, and we derived it everything, because this particular module CFD comprises of many equations, and it will help you a lot if you can recognize these equations. So now you can easily remember that this was equation of continuity. This one, rho del u del t plus u del u del x plus v del u del y plus w del u del z is equal to minus del p del x plus mu del u square by del x square plus rho gx. This is momentum in x direction. All right. Similarly, and this actually we have derived all these equations, right? We wrote it in a general form in terms of I and j, but if you write it in I, j and k separately, there are going to be 3 equations, Navier-Stokes equations, okay, for incompressible flow. Okay, so this is momentum in y direction, and this is momentum in z direction. All right. So CFD is the technique of obtaining the solution of these coupled differential equations using numerical methods. Okay. So we are refining the definition of CFD as we are going on. Initially we said that CFD is the computer solution of the flow equations, and flow equations can be many, right? Even Euler equation can be the solution, I mean the flow equations. Then we went and said CFD is the technique of obtaining solutions for momentum and continuity equation, and now we say that these equations are coupled differential equations, and you solve it using which methods? Numerical methods. I am hopeful that in your BTech course you have studied a course called numerical methods in engineering, where the different techniques are taught. We will go to the basics of that, some of them in this module as well. So, CFD involves replacing the partial differential equation, that is PDE, with discretized algebraic equation, okay, that approximates the partial differential equation. For example, I mean for example, if say there is dp by dx, so we have to replace it with, for example, delta p by delta x, or P2 minus P1 divided by some things like that. This is very basic to write, but I hope this will make it clear to you what is discretized algebraic equation. So, this is like an algebraic equation, right? So, CFD involves replacing the partial differential equations with discretized algebraic equations that approximate the partial differential equation. So, that is why there was a approximate sign when I wrote those, all right. Now, what is the solution procedure? The solution procedure in general, any CFD problems involves the following steps. First is we have to define the geometry of the flow, all right. We have to discretize the domain. We will come to it, what defining the geometry is, what discretization of the domain is, and then there is a solver stage, okay. And in the end, after the solution is solved, there is post processing. Post processing is after the results are obtained, we have to show it graphically, or we have to find some values, we have to interpret those results that we got. In most of the cases, plotting the results is termed as post processing. So, defining the geometry and the discretization of the domain, these two things are called pre-processing. So, something that you have to do before the calculation can begin in the computer, all right. Sorry. And the post processing is something that you have to do after the calculations have something to be done with the results after calculations have finished, whereas pre-processing is steps to be completed before the calculation can begin on computer, okay. So, this is the general definition of pre-processing and post-processing, all right. So, now as we said that the first step is defining the geometry. So, this step includes the creation of a CAD model. What is CAD? Computer aided design, okay. So, you use some softwares, or there are even tools available within the computational fluid dynamics models, where you can define the geometry or derive. For example, suppose for example there is a tank, right, and there is a pier, all right, and you have to, and this is open, I'm just drawing it in 2D, assume it is 3D, and flow is coming through this, right. So you will have to define this tank and this, all right. So you can do it using the CAD models, all right, and this is defining the geometry. So what does this CAD model do? The CAD model define the shape and size of the domain in which the flow equations shall be solved. So what do they do? The CAD model define the shape. Say for example, as we said, it was rectangular in shape, right? And the size of the domain. So what the length of the, for example, length, what would be the water depth, for example, here water depth, or mean your depth of the tank, actually not the water depth. I'll rub this one. And also the width in 3D. Understand? The shape and the size of the domain. So for this is a CAD model for, you see this resembles the wing of an aeroplane, for example, all right, and this has been taken from fetchcfd.com, this image, that is why we have given a reference. So as, all right, so the second step was discretization of the domain. So this process is known as grid generation or mesh generation, all right. So the process, this particular process of discretizations involves developing a set of algebraic equations based on discrete points in the flow domain to be used in place of partial differential equation. We told that the way that it is to be done, instead of partial differential equation, we try to transform it into algebraic equations. So for that, for example, if this is a domain, we need to know, so suppose we have to divide it, right, that is how we are going to write delta x, right, we have to divide it in. So let's say we have divided it into so many different parts in x and y direction. So pardon my drawing, right. So the process of discretization was developing a set of algebraic equation based on discrete points in the flow domain. So we will, so this is what meshing is. So we divide our domain into so many small parts, okay, and these are helpful because then we can actually use of these points. If you remember from your limits class, suppose del p del x can be approximated as p2 minus p1 divided by x2 minus x1, right. So this we always used to write limit delta x goes to 0, right. So this means that the grids should be as small as possible for this process to be done. Which process? That converting the partial differential equation into the algebraic form, okay. So for example, if there is a flow u coming from this side, we have defined 1.2.3.4.5.6.7.8.7, and so Ti is the strength of vortex in the ith panel. So ith Ti plus 1. So this is the way that we do, and we have taken this figure from Munsun, Young and Okishi, all right. So defining these points or forming those points using the help of computer is called the mesh generation. So the most common discretization techniques available for the numerical solution of partial differential equations are the finite difference method, the second is finite element method, and another one is finite volume method. See, we will go into small details of this so that you have a broader idea. You will not become expert overnight in all these techniques, but will give you a very good understanding and overall a holistic picture of what computational fluid dynamics is. So we'll touch briefly all of these topics. So as I said that these three are some of the most commonly used discretization techniques available for numerical solution. All right. So this is the second step in the CFD solution. First was which was the first one? If you go back and you see, the first one was defining the geometry. The second one was discretization of the domain, and as I said, discretization of domain can be done using three different methods. First, finite difference method, second is finite element method, and third is finite volume method. All right. So if you see to this figure, the continuous flow field is described in terms of discrete values at prescribed location. All right. In finite difference method, the flow field is dissected into a set of grid points. Okay, and the continuous functions are approximated by discrete values of these functions calculated at grid point. So what happens in finite difference? The flow field is dissected into a set of grid points, as I showed you, right? So this is one grid, these are grid points in x direction, this is grids in y direction. And the continuous functions are approximated by discrete values of these functions. So what we do, we calculate the value. Suppose the velocity and pressure we will calculate at this point, we will calculate at this point using our conversion of partial differential equation to the algebraic equation. Okay. This is the thing that I was trying to explain. So if this is the delta x has been the mesh size or gridded delta y. So this method is called the finite difference method. Okay. If this is I plus 1, this is I minus 1, right? This is, suppose this point is I comma j. So this will be, this point is going to be I comma j plus 1. This point is going to be I plus 1 comma j plus 1. This is how it is defined. So this is I comma j minus 1. All right. This is I plus, so I plus 1 comma j minus 1. All right. So in finite element or finite volume method, the flow field is broken into a smaller fluid elements called cells. All right. So for 2D domains, cells are areas. All right. And for 3D domains, these cells are volumes. Okay. So the differential equations are written in appropriate form for each element, and the set of resulting algebraic equations are solved numerically. So the differential equations are written for each of these elements. Okay. And the set of resulting algebraic equations are solved numerically. Okay. So we write this equation for each of these elements. If there are 1000 elements, we write 1000 equations and we solve it numerically. So this is an example where you see it's a 2D domain and therefore this is a cell. Okay. In the computational domain, it is 2D. Okay. This is 3-dimensional computational domain, and you see these are like volumes, or you can also think in a way that this 2D, for a same object we have shown a 2D representation, we can say, and we have shown a 3D representation. It's up to you how you want to take it, but the main message of that needs to be conveyed here is that for 2D domains these cells are areas, and for 3D domains these cells are volume. Okay. So I think this is a nice point to stop this lecture, and we will resume in our next lecture from this point. So thank you for listening. I'll see you in the next class.